All right, what is rhenium osmium geochronology? Let's go through the isotopes here. Osmium 188 is found in the Earth's crust in parts per thousand, parts per million. It's non-radiogenic. It's a stable isotope. It's always there. And then there's radiogenic osmium 187 derived from rhenium 187. Okay? And rhenium is found in parts per billion. So you need a really good mass spec to do this. These are anions, so you need a negative ion mass spectrometer. And there's also osmium 186, also radiogenic, but from platinum 190. We're not going to worry about the red one. We were interested in the blue, the yellow, and the black. By measuring the present-day osmium 87-88 ratio and rhenium 87 osmium 88 in a series of samples that have the same closure times, that is, deposited on the seafloor at the same time, and the same osmium 87-88 at the time of closure, which varies through geologic time as different rocks are buried and uplifted and weathered, the absolute age of a mud rock shale horizon can be determined. This is the foundation work of Creaser. The isochron is established because samples from separate locations under adjacent layers can have variations in the rhenium-osmium ratio that reflect localized microphases such as laminations, pyrite, and organic richness. Now, what makes this chronometer so applicable to black shales is that both rhenium and osmium bind with organic matter and they bind with iron and sulfur. So early diagenetic pyrite, along with a lot of organic matter, concentrates these elements in an organic-rich mud rock or shale. So as I said, the ratios of those vary in the oceans over time as different source rocks are uplifted, eroded, weathered into the ocean. Some of it's derived from hydrothermal fluids, washed in by the rivers, some cosmic dust. But basically, the isochron is like any isochron. It's based on a series of samples that come out on a line. And the best fit of that line in terms of the regression equation is what you use to determine the age by solving the math for this equation. All right? Okay, here's a view of some of these shales. Now, this is why we use boreholes. If we went to the outcrop, we would oxidize the pyrite, we'd weather the organic matter, we'd lose the rhenium and osmium. So this is our Isochron Line. Some continued work this last summer by Sean Wright. We've improved the error on this to less than 1%, which is pretty good. So 299.9 plus or minus 2.8, this is smack on with the GSSP in the northern hemisphere. So we've got now a type section for the base of the Permian, right at the glacial-deglacial transition, right at the base of this major transgression for Gondwana. This is the first absolute date for the base of the Permian in the Gondwanan continents. And it's smack dab on with the northern hemisphere GSSP. All right, so just to summarize here, we're looking again at a classic stratigraphic correlation tool, these maximum flooding surfaces where the shales extend the furthest into the continental basins, where the organic richness is at a maximum, where the water depth is at a maximum. So these are events, and now we can get absolute dates on those events, and then we can pin our floating astrochronology to a more precise time scale and really get at the same kind of frequencies, i.e. obliquity and precession, within these rocks for the very first time. And so this is how that age is found in our basins. We've got to date it here, and then we're also going to go to the Falkland Islands and date it there. And I'll just spin through these and basically show that we've got to change some of the interpretations. Here's our formation. Our age is 299, and you can see it comes right in where they're inferring the P1 glaciation. All right, so we've got to go back to that model of episodic glaciation if our chronometer is right. And we can adjust the timescales of these shales using that obliquity forcing floating chronology. And here is where that base of the Permian falls out with the red dot plus or minus the air, right at the start of P1. The black shale is the transgression. It's the end of the glaciation, not the start of the glaciation. So this tool in the Gondwanan basins, if it pans out, is going to allow us to change the timing of these and also constrain where they're occurring, where the glacials are occurring with respect to this record of PCO2 variation. I think it has some promise, and I'll just skip these because I'm running out of time. All right, so conclusions. Cyclicity in the post-glacial light carboniferous P1 interval is same time scale as obliquity, I think. and may reflect this as a forcing mechanism in the high latitude Tasmania Basin. 80 degrees south, we'd expect obliquity to be the primary forcing at that high paleolatitude. Correlation potential could be greatly enhanced via astronomical tuning in the early Permian. In the first Rhenium Osmium geochron at 299 million years supports the stratigraphic model for East Australia to Tasmania of fielding and agrees with the base of the Permian GSSP for the Northern Hemisphere. So hopefully I'll get funded and we'll get a PhD student here working on this in the next couple of years. Thank you for your time.
Can
Sorry?
you go to your second slide, the quadrant?